talking about exploiting the forest with trees, so.
All right, so just to give you a little bit of background, in many ways this is a follow-on to a presentation I gave here 5 years ago that originally had to do with using some ideas from linguistics to defeat SQL injection, but we've taken it quite a bit farther. So the fellow who said this, Tony Hoare, you might have heard of an algorithm he wrote called quicksort. He was one of the fathers of computer science, and this is from a paper that he wrote about correctness proofs of computer programs. However, things have changed pretty considerably between 1969 and today.
When in the early days of the internet, ARPANET, CSNet, etc., the biggest concern was, can we get these computers to talk to each other over long distances? You're probably familiar. Does everyone here know what Pastel's law is? Hands, come on, let's do some. Good, less than half the audience knows what Pastel's law is. Okay, those of you who know what it is, forget it. In the 70s, obviously the biggest concern for this nascent network was making sure that all the nodes could talk even when using different software, bridging different protocols. But the internet of today, 2010, is a lot different than it was 40 years ago. We have people giving their credit card numbers out over the internet. We have large amounts of certain countries' economies being dependent on internet sales. We have people actually concerned about security for their online email accounts. And I'm sure you're all quite aware that security has become a much bigger issue than it was when ARPANET was a toy project run by a couple of academic institutions and the government.
So the real question that we need to answer is it even possible to secure all of these moving parts interacting at the same time? In order to discuss this, we're going to fall back on a fairly classic model that anybody with a humanities background may actually be familiar with.
Though usually Alice and Bob aren't the examples, but everybody knows Alice and Bob. They're famous. So we've got 4 items here. We have the thought that Alice thinks. Then we have the translation of that thought into what she says. We have what Bob hears her saying, and then how Bob understands it. Now, if you look at that, you can see that there's, at every transition point, there's the potential for corruption of the information. Everyone's familiar with the old telephone game that highlights the problem that cascading errors can cause, but those errors start immediately inside Alice's head. This is analogous to the way computers talk. We've got the actual data, and then how it is encoded for delivery over the network. There can be corruption there. The recipient machine hears it, parses it, and then turns it into data that it's going to use itself. Now, the 2 occurrences of data in this, I need a laser pointer. The 2 occurrences of data in this this slide here correspond to the thoughts that the individuals in our previous example in the linguistics model have, and clearly they should be identical. In practice, that's often not the case. The biggest problem we're going to look at is right in here, where our machine Alice is saying something and our machine Bob is parsing it, hearing it. That's where you're going to find your biggest potential for confusing Bob's idea of the data from what it originally was. All
right, so when you have a serialization format, usually someone has actually written down what that's supposed to look like. Most RFCs are actually going to go so far as to have a nice BNF definition sitting in the back, so that really all you have to do is just translate that into whatever programming language you're using. But this is not necessarily the case. If you've ever taken a look at the specification for ASN1, for ECMAScript, or God help us all, HTML5, you will find a disturbing amount.
That section over there has been reserved for the auditors of ASN1, but it seems they've all killed themselves. So.
You will find a disturbing amount of information that is provided only in English, which means that the implementer has to figure out what they mean by this. A lot of stuff is actually underspecified as well. And we also see in practice that implementations tend to vary from what the specification says whenever the implementer finds it quote-unquote necessary, which sometimes means when it's convenient.
Or when the implementer's boss finds it economically important or a business case.
If you don't believe me, take a look at man7 TCP on any Linux box. You will specifically see, you will see where it specifically says that it violates the RFC 1122 standard.
Not to pick on Linux, this happens all over the place. At least they documented it.
All right, so 3 rules that I want everybody to remember. If these are the only things you take away from this talk, you're doing better than most everybody out there. First and foremost, if your specification contains a grammar and your code does not directly implement that grammar, your implementation is wrong. Even before that, though, if your protocol can be modeled as a language, but your specification does not have a formal grammar for that language, your specification is already wrong. If there is ambiguity in your specification, there is going to be ambiguity in your implementation.
Which means different dialects of implementation. When you leave it up to implementer discretion, that consigns yourself to having different implementations which will behave discretely different.
So last year, Len and Dan Kaminsky gave a presentation here on a number of 0 days that we discovered over the course of about a month in X509. One fairly straightforward example. If you have a certificate authority that uses OpenSSL for handling certificate signing requests, and a web browser that uses Microsoft's Crypto API for handling the certificates that come out of that, such as, say, Internet Explorer, you could have this situation occur. An attacker presents a certificate to the certificate authority, a CSR to the certificate authority with this really wacky-looking sequence that has it's not 2.5.4. Very large number. It's actually 2.5.4.2 to the 64th plus 1.
As the OID.
As the OID, well...
As an OID.
That's not actually an OID because 2.5. Oh, well, I'm sorry. No, you're right. As an OID, my bad. 2.5.4.3 is common name. So, 2.5.4. large number is some random OID that doesn't actually mean anything, and that's associated with www.paypal.com. Well,
the problem is OpenSSL hears it as a string literal that doesn't match CN, so it's safe. They don't have to check and make sure that its value matches anything. There's actually no logic for that. That's why it gets signed. Similar attack we found had to do with null termination. You could have www.paypal.com, null character.yourdomain.com. OpenSSL, once again, just takes that blob, checks it. It's a 3rd, 4th, 5th level domain off of the domain that you own, so it'll sign it. Then the browsers go and parse it, and they hear something different. With the null attack, which is not in the slides, but they parse it as www.paypal.com. Oh, there's a null character here, let's stop. Now, of course, they verified the signature first, and it's a valid signature over the opaque blob of data in it. And then when it's read, they do, inside the browser, a comparison to the common name string for what your URL is supposed to be and what's in the URL Chrome box, and they match. Whoops.
So in the case of Internet Explorer, Crypto API actually does that math. And at least last year, They
Why?
were only using 64-bit longs, which meant that I'm sorry, that should say 2 to the 64 plus 3. I don't know why that ported
Typo.
weird.
Right.
Anyway, that's supposed to. Anyway, the math overflows and resolves to 3, and IE says, "Oh, hey, that's a common name, PayPal.com. Great. This is a secure
Why do you
session."
need to actually be doing mathematical calculations that require a big num library over a string literal in the first place? Baits the fuck out of me. If there's anybody in here from the Internet Explorer team, oh, they're all leaving. Yeah, I'd like an explanation for that. But this particular instance has been fixed along with the 7 other or so bugs that we found last year. But the question is, how did we find all of these all of a sudden? What's our magic? Well, we're getting to that.
All right, so if you have 2 implementations of the same protocol, but they vary slightly, what you end up with is dialects that are, for the most part, mutually intelligible. This is kind of like Swedish and Norwegian. Unfortunately, the problems arise in the parts where they're not mutually intelligible, and you end up with ambiguous interpretations. In the ideal world, and because of the fact that everything should be specified in a machine-readable fashion in the first place, serialization and parsing ought to be the inverse of one another. The reason why this is important is because if you have 2 context-free grammars, or anything stronger than that, it is not possible to determine whether they produce the exact same language unless they have the exact same set of symbols, rules, and transition functions. I'll get into what those are in just a minute. With regular languages, which is to say regular expressions, finite state machines, you can determine the equivalence of those. But for anything stronger than a regular expression, that problem is undecidable. So let's talk for a moment about the classes of formal languages. This is known as the Chomsky hierarchy. So we've got regular languages, which are equivalent to regular expressions and finite state machines. These are all the same thing. The context-free languages are the same as push-down automata, which is basically a single stack automaton. The context-sensitive languages have linear bounded automata as their mechanism, and then the recursive languages map to Turing machines. So for any language, you'll have an input alphabet, some set of states, some set of transition functions, and an output alphabet. This is what formally defines a language. Okay, so what do we mean by regular languages? These are, as I said, the weakest class. And at the core, you're parsing input 1 token at a time, and those inputs cause transitions between discrete states. So if you have the regular expression AB star, then that's AB, 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 any number of repetitions of that. So I'm going to steal your cane. It can be 0 or more repetitions, so it can go from start to success without any input actually happening. Or it can be 1 repetition, so we go A, B, nothing more, we're done. It can be 2 repetitions, A, B, and we're done. You see how it loops. If we see anything else, then this will go to the dump state. And the string is not recognized.
This is the best language to implement protocols in if you can get away with it. It's the simplest to parse, simplest to show correctness, but sometimes you need something a little more powerful than this.
We'll be talking in a moment about situations where you might need a stronger class of grammars, and in fact, what class most protocols fall into. All right, so the next step up is the context-free languages. With the context-free languages, you get recursion. It's not actually possible to produce a finite state machine that generates A to the n, B to the n, which is to say a string with the same number of A's and followed by the same number, some number of A's followed by the same number of B's. It's implemented as a stack, and in fact, the tree looks very much like a stack. And so you can literally read the string just by doing a just by doing a post-order traversal of the tree. Context-sensitive languages are generally written in a format that looks very similar to context-free languages, but the non-terminal symbols, which is to say any symbol that branches off to something else, anything that's not a leaf node, those can also show up on both non-terminals and terminals can appear on the left side of a production. Basically, this means that you can maintain context within as the parse is going on. One example of that is length fields. In an HTTP packet, for instance, you've got a content length header, which must correspond to the actual length of the payload. And then the next step up from that, you've got the recursive languages, which are Turing complete, and this is where we run into the undecidability that I mentioned earlier.
Yeah, writing your languages in a Turing complete. If your protocol is equivalent to a Turing machine, you probably have given it more power than you need. I mean, there are instances where that is the only language you can write this protocol you want to write in. But when you wind up in that kind of situation, you should usually try to think, well, can I break this up into two context-sensitive languages that achieve what I want? Or is there a way I can bound the power of this somehow so that I don't wind up with an undecidability problem when I'm trying to make sure that I'm parsing this correctly?
The reason why undecidability is a problem is because it is literally not possible to tell what a program will do with a given input unless you run it. That's the only way to know. You can't predict. You don't know if the program is ever going to terminate.
Examples of languages that are Turing complete that shouldn't be. XSLT. That one will break your head, but think about it.
All right. So as we were discussing earlier, we can look at the internet as a very large composition of languages. So there's this concept in mathematics called closure. If a class of things is closed under a certain property, then that means that if you apply that property to any one or more entities in the language, or in the class rather, the result is still in that class. So when we say that the regular languages are closed under composition, that means that if you compose two regular languages, then the resulting language is also regular. This is also the case for the context-free languages. Some of the context-sensitive languages this is also the case for, but only the ones that you can specify with a parsing expression grammar. And I'll talk about those a little bit more later. If you compose two context-sensitive grammars that cannot be modeled with a parsing expression grammar, no guarantees. You could very well end up with a Turing-complete language.
And of course, if you compose something with a Turing-complete language, well, you've got a Turing-complete result.
Yeah. I mean, one thing we're actively working on right now is trying to define parsing expression grammars for every protocol we can get our hands on. Because we really want to know, is the internet decidable or not?
And the next step from that, of course, is when you write your RFCs, you include the reference grammar so that the implementers can see if they're parsing correctly. If they're all building their implementations off the same reference grammar, they're not going to have differences. We'll get more to the sort of attacks that leads to when you don't all work with the same grammar in a bit. But
all right. All right. So this applies not only to people who are designing protocols, but to people who are designing systems that use protocols. And when I say protocol, I don't just mean network protocols. I also mean file formats, I mean serialization formats, anything that can be specified as a language.
Anything that, when you're operating with it, it falls into that Alice and Bob communication model. So reading a JPEG file is really no different than the problem of reading incoming network traffic in this way of looking at things.
So when you're composing languages of different types, languages with different strengths, you will end up with a result that is in the stronger of the classes. So if you're going to compose a regular language and a context-free language, the result will be context-free. And there are some nice formalisms that you can use for actually implementing these. My personal favorite at the moment is parser combinators, which are those came out of Haskell, but they've started to appear in other languages as well. They're now available for Scala, Java, Python, and F#, which means by extension the rest of .NET. So another thing that we're actively working on is can we take a machine-readable specification of a grammar and translate that into a bunch of parser combinators that produce a parser that you can then hook into. Unfortunately, you're not always going to have the ability to restrict yourself to things that compose nicely, but if you can, do it. But this is not a defense talk. This is an attack talk.
So, buffer overflows, yawn. One of the things that the approach that we're taking gets us is if we were to look at this, and if it were a defense talk, we would talk about how implementing strict grammar parsing made it so that 90% of buffer overflows would not be reachable by an attacker. You could have them, you could be there, but if the attacker can't inject a payload, then they are not an attack vector. Well, the flip side of that is we can use these techniques to find where there are likely attack vectors. We're examining these protocols and the implementations of them, not in search of a specific attack, but in search of simple weaknesses. Can we find automatically or with a tool-assisted methodology the areas in an implementation where when you tap on the wood, it's rotten? And the answer, of course, is yes. There's a number of classic problems. The implementation isn't able to differentiate between data and code. That's the fundamental problem that leads to any kind of injection attack. The recipient thinks that it's got a safe input and it's parsing it, and somehow something that's supposed to be put in the data only section gets interpreted as code, executed, and potentially bad things happen. Back to the classes of language, SQL is a context-free grammar. So actually parsing that to make sure it's context-free is trivial. Regular expressions and so forth, of course, are not good enough to stop SQL injections because they only work, for sure, on regular languages. When you go to a higher complexity, you need a higher complexity parser. Not sure where you're going with this slide.
So another place, another interface, another boundary that tends to be ripe for problems is when you have multiple implementations of the same protocol. This was what we had a lot of fun with last year between NSS, Crypto API, and OpenSSL.
Because you wind up with a situation where they're not all speaking the same protocol. They're all speaking versions of the same protocol in most cases, mutually intelligible dialects. However, if you can wind up with situations where one implementation of the same protocol parses the same input data in a different way than a second implementation of this same protocol parsing this same input data. You now have, first of all, proof that they're not identical, and secondly, you've got a point of weakness. We refer to this as differential parse tree attacks. We'll have a slide on that later, but this allows you to pinpoint the area where there's likely to be some maneuverability to build an attack. This is where your attack vector is likely to be, because you can confuse the recipient by crafting an expression of some sort of payload for this packet so that it means one thing that's safe to the one implementation. In our X509 stuff, we had the problem of, as I mentioned before, OpenSSL pretty much doing things correctly. Parsing things as they were. We've got our string literals here. We've got this null character. Obviously, that's a character. We're going to treat it as such and validate against everything after that. I mean, we're not going to ignore it. The problem, though, was we got special rights based on that, the signing of our CSR. And then when we turned around and had a different implementation parse those same parts, they parsed them differently, and differently in such a way that it escalated privilege for us. So had OpenSSL been doing things as identically but as haphazardly as the browsers, the attacks probably would not have been possible, or most of them.
I mean, it's a little bit unexpected, but if everybody's doing something wrong the same way, then it's actually not as bad. If one person is doing things right and everybody else is doing things wrong, then you actually end up using the you end up
play them off of each other.
You end up playing them off of each other.
And it's not just limited to two different implementations. We found with OpenSSL, particularly with open source projects, but also long-lived commercial projects. You guys are familiar with this. There's an implementation for parsing this stuff, but it wasn't written initially in a very generalizable way. So rather than use the existing code, you go and rewrite the parsing for it in a more flexible way or tailored more toward your new use case. And you wind up in a situation where, depending on whether the application is called from the command line or from a library or given a certain switch or whatnot, you can actually access different code paths in the same application that do the same identical thing. And if you're really lucky, they do them differently. So you can actually play an implementation off of itself if you call it in a different fashion. Question?
Where you have a 32-bit version and a 64-bit
Yes.
version and they overflow to places?
Yes.
But it's not just differences in overflows, which is always going to be there. But right now, we're dealing with the situation where you can presume that a 64-bit application is aware of modern security techniques. For instance, a number of the introductions to Vista that actually make doing buffer overflows and code injection in that way more difficult with memory randomization and so forth are only on default for the 64-bit, because you can assume that they're going to know that. You can't assume that on 32-bit. So often there's other differences between what functionality one class of an implementation is going to have. I mean, the problem doesn't just exist with the 64-bit versus 32-bit. It's also what compiler, which usually isn't a problem for commercial software, but is de facto a problem with most open source software implementations, because you can't always guarantee that every instance is going to be compiled with the same compiler. And of course, as you know, your compiler is going to make a difference on how your code structures are handled. And if you don't actually take precautions to make sure that the compiler doesn't change how you're parsing things, you may wind up with a different parse depending on what compiler options or what compiler.
All right, so let's take a closer look at each of these different boundaries. The first one we're going to talk about is the data code boundary. Every injection attack ever is a confusion between data and code. Almost always, it is data being misinterpreted as code. I mean, so this is the case for SQL injection, LDAP injection, XPath. It's also the case for cross-site scripting, because in cross-site scripting, you have elements being inserted into the DOM, and those could be a script element, which if it then gets executed, well, there you go. You've got supposedly data being executed as code. And despite the best efforts of the same origin policy, once an element gets into the DOM, that's it. It's game over. If you've got an element, I mean, JavaScript can be modified on the fly. It's like Lisp. You can write self-modifying code in JavaScript. I haven't seen a self-modifying XSS exploit, but if any of you write one, I'd love to see it. It would be cool. So
start with Dan Kaminsky's self-modifying code that uses the same MD5 hash. He's published that at Blackhat before, so that's a good template for you. Please break stuff for us.
So what you want to look for when you are auditing a system to find these potential points of weakness is any point where you've got one component emitting a serialization, taking data that's in some binary format and moving it onto the wire, or moving it into a text file, just moving it into some kind of marshalling format for something else to pick up and either use as data or use as code. If it's going to get parsed, there's always and if the component doing the parsing has the ability to execute things based on what it's parsing, this can be a big problem. So this is another reason why we strongly recommend writing using the weakest language mechanism you can possibly get away with.
You may have seen we've been mentioning HTML5 a lot. I don't want to go on record saying what I'm about to go on record saying, because I haven't proved that HTML4 is not Turing complete.
It's not.
We think it's not. We're pretty confident it's not. We haven't sat down and done the proof. But let's just, for sake of argument, say HTML4 is not Turing complete. HTML5 is. So they've just gone and made a validatable language unvalidatable.
You have WebSockets for pulling data. You have browser-side storage that you can use as a tape. Yes, if you have to, God help you, you can actually use the classic, 1950s Alan Turing model of a paper tape. People have done this in the obfuscated C contest. I'm not kidding.
You guys want 0 days in HTML5? My intuition says look at the differential between Canvas implementations on one browser versus another.
But yeah, you have the ability to pull down data, you have the ability to write it to a tape, and you have JavaScript that will execute it. So that's all you need.
Furthermore, HTML5 without JavaScript is still Turing complete. So turning off your JavaScript isn't going to save you this time.
Yep. So another pain point that you're going to want to look for is places where you should just be accepting a small subset of some language. We'll get into this more later on in the talk, but the most common example these days is actually the RESTful APIs that in web applications, because all of those every call is going to be an HTTP call, but only only a small subset of the entire possible universe of HTTP requests is acceptable. So what you really want to do on the defense side is constrain what you're willing to accept. On the attack side,
Of course, no one does that. So
no one actually does that. So on the attack side, what you want to look for is places where you can send something in a very expressive language, and people are not necessarily going to be expecting things that they didn't predefine. But it's more fun, at least in my opinion, to take two implementations and say, let's you and him fight. So if you can find an input that produces a certain set of state transitions and a certain output in one implementation, but it does not produce the same set of state transitions or the same output in a different implementation, bad things can happen. The vast majority of TCP/IP vulnerabilities actually fall into this category.
We're talking about old ones from the 80s, early 90s. That was actually they were doing what we ended up formalizing for the X509 attacks, but that's what made us hit on it. I think it was Dan Kaminsky who said, wow, this is all, everything old is new again. And sadly, it didn't stop being old. It just stopped being paid attention to. We've been playing whack-a-mole with these sort of problems for 40 years now. When I give my how to write code in a secure fashion so that it doesn't fall victim to these sorts of attacks talk, I basically have to sell the idea that we need to completely redo the way we think about writing software. We need to have a paradigm shift in how we conceive of the art of programming. Well, I don't think that's going to happen by next year or 5 years from now. Maybe in a decade, but that's why these attacks are going to be here for a while. They're here to stay. So when you're going out to look for this, first of all, be overwhelmed by what protocols do I start with? Where do I start here? Maybe you're actually an implementer of a certain protocol and you want to make sure that your implementation doesn't fall into these problems. But remember, you've got to audit everybody else's implementations that are supposed to interact with yours because of the composability observation. If you've got code that relies on being a part of a secure system, then you need to actually make sure that all those parts are secure and realize that your security is, again, only as strong as the weakest member of this system. So if you've got a system that has, as a fundamental part of its security model, the requirement that two implementations actually behave identically or interpret the same input in the same way, be it firewall rules or X509 certificates, or just simply respecting code and data boundaries on input, SQL, and so forth, then that's an area where you're going to want to apply these techniques. Now, Meredith mentioned that you have trouble if your one implementation produces a different parse and output as your second implementation. Well, you don't need to pay attention to the parse at first. If you look at, if you find an instance where one algorithm that's supposed to be identical to a second algorithm produces a different output than the second algorithm when given the same input, you know that you've got a difference in your parses. That's the only way you're going to wind up with a different output. So at that point, you back up. You find where that actual linchpin point of difference is, and that will guide and inform your development of an exploit. Now, we're not going to go into the various different types of exploits that you can build for these sorts of things because it is always dependent on what vulnerability you find and what your end goal is, of course. But if you guys are exploit developers, that would probably be stuff you already knew anyway. The point of this talk here is to tell you how to find a novel method of finding areas where there are likely to be exploitable weaknesses, and the methodology for doing so.
In particular, you don't want to just look at the code, and you don't want to just look at the binaries. You also want to look at the specifications, because when a specification is vague, as we said earlier, this means that you will have differences in how things are implemented in the wild. Don't just look at what the implementation includes. At what the specification includes. Look at what it leaves out.
In X509, for instance, we had the problem of, well, first of all, there is no X509 implementation that actually makes use of multiple values for common name, to my knowledge. Anybody knows different, please tell me. Fourth talk I've said that and gotten no hands. But the spec allows multiple values for CN. However, both the ITU and there's actually one RFC written, the IETF RFCs, that has guidance for how to handle multiple CNs, multiple values for CN. And I believe it's something, I wish I had the quote, but it's something about as useless as use the one that makes the most sense. So is that the first one? Is that the last one? Is that the middle one? Is that the one that's evenly divisible by 17?
Roll the dice.
And of course, this led to one of our attacks in the X509 because you've got different implementations looking at the one that makes the most sense differently. One browser takes the first one browser takes the last one browser tosses a coin, and you wind up with you submit your CSR to your certificate authority, and it picks the first one, and and you know it's going to pick the first one, so you put your innocuous, legitimate common name in there, and then you target everybody that's using, I think Mozilla was the one taking the last one, so you target them with that, and you do the reverse when you want to find, when you want to attack people running IE.
All right, another question.
It seems to me that most SQL injections and HTML injection attacks take advantage of code that isn't really serializing anything at all. It's just adding a bunch of strings together, and some of those strings are escaped, maybe.
That's still a form of serialization. I mean, I'm using that term just to mean data. Data that was in memory gets written to something that we can send it to other people with.
Okay.
Yeah, it's. The serialization is just the process of getting it from in the human language model, it's from your head into the air.
Into a sentence.
Like when YouTube had that problem with the comments having code injections into it.
I liked that one.
They thought they scrubbed it, but they didn't do a good job, and it left stuff through to put it in the right way.
Well, that's the problem. Is you can think you've put in place protections against injection using regexes. And you can catch, you can make it a pain in the ass to do an injection attack if your language is context-free and you're using a regular expression whitelisting or blacklisting approach. But you simply cannot, you can't make a proof that says that's going to ensure that we've parsed this correctly, because the actual interpreter that's going to generate, to make use of the code that you're or the input that you're trying to sanitize is computationally stronger than the blacklist, whitelist filter checker.
The only strong guarantee is to use a regular expression to accept something and only that, and then discard everything else.
Well, really, the right way to do it is actually context-free whitelisting, which is to say, come up with a restricted sublanguage of, well, in this case, we'll say HTML, that only includes generation rules for what you're willing to accept. So, for instance, you would disallow any production that contains the script tag. If you can actually view you can actually view not just a parse tree but a language as a tree. If anybody's ever taken a look at a Bison file or a Yak input file, you've got essentially this hierarchical list of production rules. And if you remove production rules that produce symbols that you don't want, then you can keep those from being recognized, and you don't end up with a situation where a cleverly crafted input can get past your filter, because anything that would need to apply one of the production rules that you got rid of in order to be parsed will be rejected completely. But you have to match the computational strength of your input language.
Match or be stronger than.
Match or be stronger than, but it's really preferable to match it exactly. Okay, so we
Injection attacks against your grammar verifier, they're just embarrassing.
yeah. Question.
A lot of languages need to be written by humans, HTML and CSS do, and they can't just reject things. Instead, the CSS specification and HTML4 didn't, but HTML5 does specify what browsers need to do in error cases, and that makes it harder to do what you're recommending, to have the serializer and the parser use the same code based on that grammar.
Are we talking about the restricted sublanguage stuff, or are we talking about just in general?
In general.
Well, so I mean, if you're, I don't see any reason not to use the same parser code but have different hooks. Because if you treat parsing as validation, as simply the recognition of whether, is this actually a valid string in the language that the parser is for? That's really the first question that any parser has to answer, and a serializer has to generate a string that is valid in that language. I mean, generation is really just parsing backwards.
The HTML5, every string creates some DOM.
Sure. Maybe we should take this offline because I'm not sure I follow what you're saying. All right, so 3 general classes of attacks: ambiguity, nonsense, and confused deputy. Ambiguity we see a lot in the English language as well. There are some really hilarious lists of headlines that parse differently.
British push bottles up, German something.
Rear.
Yeah, it's a headline.
Yeah, from World War II. The British the British surged into wherever it was they were fighting the Germans, and they overtook them from behind and bottlenecked them in one place. So British push, bottles up, German rear. Nonsense attacks are when you basically throw semantically meaningless bullshit that just happens to parse at an underspecified language, and see what you can get the implementation to do.
A lot of fuzzing falls into this class.
Yeah, fuzzing generally tends to be nonsense attacks, and
even smart fuzzing, though, that also takes advantage of ambiguity and confused deputy as well. But
yeah,
the original definition of fuzzing, the dumb, let's just throw junk at this until it rolls over and says, fuck me. That's a nonsense attack.
And confused deputy attacks. These actually got their name in the capabilities world. Blanking on the name of the guy that came up with them, but Norm Hardy. Thank you, Brian. Yeah, pretty much everybody ignored them.
It's capabilities, right? It's not worth paying attention to. But we'll take the terminology because
it happens to be the case that cross-site request forgery is a confused deputy attack. The idea here is that because you've got an embedding someplace that it's not supposed to be, whatever entity that you've delegated some authority that you have to doesn't realize that embedding is not where it's supposed to be, and not even supposed to be there in the first place, and just goes ahead and does stuff with it because it thinks it's doing the right thing. So it makes sense that this would come from capabilities, because they're all about making that not happen. They're all about keeping things nicely locked up in their own special corners. Okay. Okay, so we can see ambiguity in different places, not just between input and output, but also between the internal states of implementations. The integer overflow attack that we described earlier was an example of an ambiguity attack. It was syntactically valid in both dialects. The parsers were in fact different. It's also semantically valid, but what the sender intended and what the receiver understood, the semantic content, the data, if you will, those will differ between implementations in an ambiguity attack. These are kind of, they can be a little difficult to identify because you have to have a really solid understanding, not just of the grammar that you're dealing with, but also the back-end state. Yeah, so it's not enough just to have the TCP packet specification down in your head. You also have to be thinking about, okay, well, what happens if I throw out weird stuff in a state? What happens if I throw out a totally valid packet from a state that packet shouldn't be sent from? However, once you locate the place where a misunderstanding will occur, the path forward is usually pretty obvious. Nonsense attacks, on the other hand, are going to be syntactically valid but semantically meaningless. Classic example of this is the good old-fashioned TCP Christmas tree packet. If you're in a listen state and you receive a packet with the SYN flag set, that makes sense.
Let's point out that that's syntactically valid from the point of view of the parser, not from the point of view of the protocol. Obviously, anything that's not syntactically valid is just going to be rejected. However, you can get syntactically invalid, according to the protocol, packets through an implementation if it mistakenly takes them as syntactically valid. Just a point of clarification.
Yeah. I mean, the specification, the TCP RFC actually doesn't say anything about, well, what happens if you light up every flag. There are some mentions of like, well, okay, you're only supposed to send SYN at this point, and if you're sending that, if you've got the SYN flag set, that's probably not right. And you know, but it doesn't specifically say that if you get if you get a set of flags that are not valid for whatever state you're in, you know, that you should. You know, it doesn't say what to do with it.
Here's where I'll take the opportunity to define Postel's law for those of you who didn't know it. It's be conservative in what you generate, but liberal in what you accept. Now, RFCs that don't specify what you should do when bad stuff is generated are probably written by people who are strongly thinking that this isn't going to happen, because that's a Christmas tree packet is obviously not a conservatively generated packet. However, Postel's law was formulated in an era before worrying about what somebody who wants to fuck shit up on the internet is going to do became an actually, valid driver for design requirements. These days it is, but we're still in the mindset of, well, the implementations will figure it out themselves. And on the flip side, the be liberal in what you accept basically says, have your implementation speak multiple dialects that might conflict, because it's better than incompatibility.
Now, it's important to observe here that when you have these kinds of variations between how different implementations handle nonsense input, you can actually use that for fingerprinting. I mean, that's what Nmap does. So here's another nonsensical example with PKCS1. So back in 2006...
The padding for signatures with S-MIME and so forth.
Right. So back in 2006, Daniel Bleckenbacher shows up at Crypto out in Santa Barbara, and proceeds to explain how he could forge RSA signatures. So an RSA signature is supposed to be padded with FFs out to the width of the modulus. So you've got the signature, but the entire thing needs to be as long as the modulus is, and whatever's not actually data just gets padded with well, it's 00, then 01, then a bunch of FFs. So what he was doing was shrinking the padding bytes, because after the padding bytes comes an algorithm identifier and then the hash. So what he was doing was shrinking the padding bytes and adding a bunch of extra shit after the hash, such that the tail end resolved to a signature that was valid, that was quote unquote valid, but not actually, but had not actually been signed by the right key. I mean, happily, this only worked for small moduluses.
Because he adds enough garbage that the resulting signature is to the power of the exponent in such a way that you can actually then use E to factor it. So you wind up with a cube of what you originally had, and that's going to be handled by most implementations of RSA. E equals 5 might be, if you're able to handle, I can't do the math, it's a 5-figure long RSA key. There are some implementations that handle that, but E to the...
So 2 to the 16th minus 1.
2 to the 16th minus 1. That you're not going to ever run into trouble with in this case. But the problem here had to do with the parsing of the pattern. Again,
really what was happening was it was a length field mismatch. You're supposed to have the length of the padding is supposed to be dependent on the length of the hash and the length of the and the width of the modulus. This is something that could have been represented with a context-sensitive grammar. So we could have done context-sensitive parse tree comparison.
in fact, we did.
Yeah, that was in fact what prompted us to extend the context-free work that I did back in 2005 to the context-sensitive languages. But
we implemented the parser that validated that the padding was correct, and tried to get the exploit through on vulnerable code. But in our case, even though the padding parser that is in OpenSSL was broken, and also NSS, we were able to stop that code from getting to that point. So this approach, if it's actually implemented correctly, allows you to have broken, buggy, attackable code that can't be reached by the attacker in most traditional means. This particular example shows that it's not just, so all the X11 attacks we did were all pretty much not crypto attacks. We left the crypto alone. This one is one where it's both a file format and a crypto attack, because you've got to know some properties about RSA in order to be able to leverage the mistaken parsing of the padding in order to get yourself what appears to be a valid RSA signature. So again, this is an example of why we're not picking out specific, recipes for forming attacks. You've got to use you've got to look at whatever case you find, where you find weaknesses, and be creative. Figure out what's being given to you here and how you can leverage it.
all right, so cross-site request forgery and its friends. So you've got some web application. As we said earlier, the set of operations that make up the web application is going to be a restricted sublanguage of HTTP. The input alphabet is smaller, it's got fewer states, fewer transitions. However, it does still have all of the same tokens that, that are available to HTTP, but if you have them and don't use them, it's like not having them at all. The referrer header is the one that matters for cross-site request forgery. If you're ignoring referrer headers, you are reducing the strength of your validator because you are dropping the context. It's supposed to be, there should be some context sensitivity here, but you're dropping that context and literally changing the grammar that you're actually implementing. All right, so we mentioned parse tree differentials earlier, and we're going to get into those in more detail now.
So, as I mentioned a couple times already, different protocol dialects, i.e. different implementations of the same protocol done by different teams, even if the protocol itself is written perfectly, unless you've got some test vectors, which we do. I mean, if you want to look for examples of where test vectors have been used and used well, crypto algorithms. If you implement a new hash function, one of the things you have to do is provide a test vector so that somebody else who implements your hash function can provide it the test vectors that will produce output that match what they're supposed to. What we're suggesting people ought to do is provide a grammar that can be used to validate the parses that you've implemented. That should go with the RFC or this implementation spec or what have you. It doesn't. There's some RFCs that do a little bit of this, but not in a complete, all-encompassing way. So, as I said, even if your RFC is done perfectly, there's no ambiguity, you still have different teams implementing it, potentially going to do it differently, different tools being used, which may introduce stealth differences when you compile, so forth. Particularly, edge cases here are your friend as an attacker.
This is why vagueness matters, and this is why you should be conservative in what you accept.
However, even if your implementation is not vague and you're being conservative in what you accept, if you've got a different way of handling the input than the other guy, i.e. if the other guy's not being conservative in what he accepts and he's got a problem, because of the issue of composability, if you rely on him doing things right, you're in trouble. So, how do we actually leverage this to find attacks? This is easier if you've got access to the source and you can actually look at the parsers. If you need to do this against a closed source binary, we're actually looking at implementing a tool inside Valgrind to do that. But our current methodology is to take the call graph and derive from the call graph the parse tree for a specific input.
And we do it by hand, and it totally sucks. If anybody saw Ben Nagy's talk earlier today, I didn't actually catch it, but I'm planning on going and talking to him because
the idea is to not do it by hand. That's what the Valgrind stuff.
Yeah, well, I mean, so what Ben's doing is looking for he's basically doing a lot of fuzzing and then tracing through call graphs to find out what makes things crash. This is similar but different.
So you've got your two different parse trees for your two different implementations. You want to look at them, find the points of difference, find the inputs that will get your code or get your input packets to those points of difference. It's basically get them parsed far enough that they have to be handled by the areas that differ. That's your weak point. That's your attack point. That is where you're going to have fun. Because everything after that now is an opportunity to confuse one or both of the implementations. You are able to perhaps get code past an IDS that emulates the target system, but does so in a slightly different way. if you're aware of what that way is, because that way you can create a packet that's going to come in, be validated by the IDS, and then passed on to successfully attack the target. This, again, is the fundamental way that we did most of our X11.9 attacks, because we were able to take a malicious CSR, submit it to one implementation that went, oh, you're fine, you're not malicious, you're cute and fuzzy, I'll sign you. And then we turn around, send it to the target, and the little bunny bears his fangs. Does everyone get that? Why parse tree differentials are a boon to smart fuzzing and are a big bright light on where your targets are? This does not guarantee that you're going to have an exploit in that point. It does not guarantee that there's not going to be stupider exploits somewhere else, but it is going to give you, particularly in instances where you're dealing with a huge application that's got thousands of lines of code, and if you just start chucking garbage at it with dumb fuzzers, you're going to be there forever. This gives you a way to narrow down where you want to be spending your time. It's an optimization for attackers. And furthermore, when you do find an attack like this, it's usually not a classic attack that most people
Have already heard
of, or there's an easy fix for. It's usually throwing a spanner in the works, and particularly for applications that are absolutely dependent on being able to speak to other implementations of the same protocol. If it's a client-server model, or if it's peer-to-peer model where there's different implementations. When you're faced with an attack where the answer is do it incompatibly from everybody else, you've just put your target in a really bad situation, because they can fix the bug and now be broken in that they can't talk to anybody else. They can not fix the bug and be screwed, or they can try to do a very messy, very prolonged vendor coordination approach to everybody fixing the bug in the same way, let's hope, so that there's not any problems with compatibility. This is why we had all those X509 attacks done in January, and we actually couldn't talk about them until August. And that was against an industry that already has a big, let's coordinate our security problems group. VeriSign has been very good about that. We actually only had to talk to VeriSign and Microsoft. They did the rest of the dissemination for us. And it still took 9 months.
Yeah.
Now let's imagine this is browsers and web servers. I can't even count the implementations that are out there.
Is there even any point to going after browsers since they're already an open? You already established that it's an open language for complete thing.
Well, yeah, because that tells you that you've. It tells you that you're going to probably be successful.
Yeah, pretty much.
Well, that's the thing, but like knowing that anything is possible, doesn't really constrain you to any potential vulnerabilities. Could be anything.
Well, but you still have to figure out where how you're going to get in. You've got this attack surface, but you still have to find the places where where you're actually going to trip over things.
Just because it's not provably impossible to break into something, and just because it's provably not impossible to break into something, doesn't mean that it's easy to break into something.
And remember what I said earlier. If everybody's doing something wrong in the exact same way, you're in better shape than you would be if some people are doing it right and some people are doing it wrong. All right. As I also mentioned earlier, we're also working on the defense side, figuring out a specification for grammars that are both human readable and machine readable. Something that it's easy for just anybody with anybody who's thumbed through a basic computability theory textbook to write up some BNF that can then get parsed. That can then get fed into a parser generator, which generates code with with backend hooks in whatever language you want. I'm working on something like this already in Haskell, and once that actually works, then you've got the foreign function interface, and furthermore, parser combinators have been ported to a whole bunch of different languages, so it'll be easy to move that over to Java and .NET with and hopefully thereby minimize the differences between implementations cross-platform.
We were hoping to have some examples of new, I was hoping to drop 0 days here, but as I said, the coordination is quite difficult. But I expect that, first of all, I'll have 0 days to show the next time I see you guys, perhaps at Blackhat Europe next year. But I'm hoping that people in this room, people you know, if you point them at this talk, will start actually looking at this as a methodology for finding areas of weakness. I don't spend most of my time doing fuzzing and doing exploit development, but some of you do. How much time do you spend just wasting your time while your fuzzers go through a million cycles trying to find an area where they can actually get something that's promising, or sitting through reading code looking for user mistakes?
I will tell you we've got a head start on HTML5, but I would be thrilled to see some of you guys catch up to us and pass us.
HTML5 is enough problems. Enough problems to feed everybody in this room.
All right, so any questions? Or did we get them all during the talk?
Yes?
So you had the three categories.
Uh-huh.
Is that just because 3 is a nice round number?
Yeah.
Like, do you have a couple more maybe that would be good to look at too?
You're talking about ambiguity, nonsense, and confused deputy?
Yeah.
In general, those have been the categories that things we found have just fallen into.
95% of what you find falls into one of those.
They're pretty broad categories. And again, I mean, this is a methodology talk. Our goal is not so much to give you specific things give you specific detailed concrete things to look for, as to change the way you think about what an exploit is.
I'm confident that there's other exploits that fall into a class other than those 3, and I'm confident that there's exploits that have not been described before.
But I mean, really what it breaks down to is you've got syntactically valid, semantically valid, but semantically valid but different, and then syntactically valid, semantically invalid, and then we actually threw in confused deputy at the last minute because it was like a week and a half ago that I realized that cross-site request forgery actually falls under this paradigm as well. Okay.
Any other pressing questions? Can I take one more? I mentioned
oh, yes, we have.
I mentioned XSLT only in passing because I'm writing a paper on it, and I don't want one of you to scoop me. But
we should talk about the control characters. The control characters are hilarious.
Yeah, we're out of time, but catch us after. Come up afterward, and XML is
short version. Control characters in XML. You can change the encoding up on the fly, and then change it back.
That's just one of the problems with XML. XML is a playground.